Well, good morning, everyone. My name is Larry Gastiger. I'm the Executive Director of WIRES, and I want to welcome you to this latest in our series of webinars that are focused on various advanced technologies and how they impact or integrate or work with the grid. So I'm very pleased today to welcome Ampacimon, who's one of our newer WIRES members, and with them is Brian Berry, who's the Chief Product Officer for Ampacimon. Brian's going to give a little bit of an overview about dynamic line ratings. I know we've had some discussion about this before, but I think it's helpful to get some different perspectives on this issue or this topic. I want to mention to folks who are watching that Brian will go through a presentation. He has a slide deck that he will walk us through. And then at the end of that, there's an opportunity for folks to submit questions. I know Brian's looking forward to getting different questions from folks about the presentation. All you need to do is use the question function on the right hand of your screen. If you click on that and type in your question, we'll have it and we can go through that at the end of Brian's presentation. So with that, I'm going to go ahead and turn it over to you, Brian. Welcome and thank you for coming to talk to us about dynamic line ratings and how they can help integrate more renewables into the grid and benefit customers.
Great. Well, thank you very much. And I'm very happy to be here on Valentine's Day. So happy Valentine's Day to all of you guys. And in true Valentine's Day fashion, I apologize for catfishing you with my 5-year-old photo. I'm a little bit older. Sorry about that. I'm not sure I'm wiser, but there we go. So today we're going to talk about dynamic line rating, particularly in the US, but also around the world. And let's just get this working. I'm going to talk today a little bit about Ampacimon just to introduce you to us. Then I'll give a brief introduction of what DLR is, so everyone's on the same page. And then we'll start talking about the benefits and the regulatory frameworks around that. So we'll have some benefits for utilities. We'll also have benefits for society, so lower electricity prices, how that works, what it looks like. We'll talk about the great work that FERC has done so far in the US, and then I'll try to make it really real with some case studies all around the world of various types. And then we will end up, I'll just summarize and we can go into some Q&A. So please get your questions ready. Really happy to have a lively discussion. So to introduce Ampacimon, we are a company that's been around since 2010. We've got 3 legs in our company. Capacity optimization, which is the dynamic line rating leg. It's all about getting more capacity out of your assets. Asset health, we talk about our product suite called Grid Life, where we look at assets in terms of partial discharge monitoring or condition monitoring, and we try to predict any sort of failure to assets. And then lastly, grid reliability, which is Grid Visor, where when the lights are to go off, if it were to be in distribution, for example, we can do some root cause analysis, we can understand that, give you some situational awareness and help you to restore the power as soon as possible. In terms of the suite of assets we work with, overhead lines, underground cables, and then of course, substations, switchgear, and motors and generators. We are headquartered out in Liège, Belgium, in Europe, and then we have another R&D office out in Madrid, Spain. So the Madrid, Spain office is dealing with the asset health side of things. The Liège office deals with the capacity optimization and overhead lines. In America, Atlanta, we have a sales and project office, and you can see a couple of big utility names there. One of our flagship customers within the US is PPL. We've done some DLR work with them for a couple of years, and they did win an Edison Award for that work last year. A few other big names in there, as well as in Europe, and you'll see some of these names come up throughout the presentation. So let's talk a little bit about DLR. Okay, so DLR in essence is the idea of when you have an overhead line, you have a piece of metal in the air, and that piece of metal has got 2 heat sources, and 2 heat sinks in simple terms. The heat sources are either solar heating, so heating from the sun, or heating from the current on the line. So the more current you push through the line, the hotter it's going to get. But then you have 2 cooling sources or sinks, if you like. The one is radiative cooling, which is ambient temperature drives that. So if the ambient temperature is cool and colder than the conductor, you'll actually have a cooling effect. And the other one is convective cooling, which is from the wind. The wind blows over the line and causes it to cool. If we look at the size or the quantification of these different elements, you can see that ambient temperature, this is from Department of Energy report a couple of years ago. You can see that ambient temperature is approximately 2% change for a 2 °C change. So that's about approximately 1% for every 1.8 degrees Fahrenheit change. Solar radiation has a difference of, if the sun was shining, middle of the day, no cloud cover, versus complete eclipse or middle of the night and nothing else has changed, 18%. But then we look at wind, and with a wind of 3 feet per second, now 3 feet per second is not a gale force wind, it's not a heavy wind at all. If you were to walk down the street on a calm day, that's what you're feeling in your face. It's it's 3 feet per second or 1 meter per second roundabout. So it's a very light wind, but that can give you up to 44% extra capacity on a typical conductor if it is perpendicular to the conductor. If it is 45 degrees to the conductor, it still gives you 35%. And even if it's in parallel to the conductor, it still gives you some cooling. So the key point here is that all of these different environmental impacts have an impact to how much capacity you can push through the line. But by far, wind is the biggest contributor to cooling and something that is not easy to ignore. So now we get into the different types of ratings that are used around the world. So starting at the top, your typical rating is static line rating. This is when you buy a conductor, you'll get a data sheet that comes with it, and it says, this is what it's designed for, do not exceed this value. And that's conservative. It has to assume the the hottest time of the year, no wind. It's very, very conservative. Many utilities for a number of years, decades even, have used seasonal adjusted ratings, where they take into account the fact that winter is a lot colder than summer, and they essentially use different weather parameters to determine the rating in the middle of winter and the middle of summer, and they swap over between the two. So you land up with this higher rating in winter, lower rating in summer typically. Moving one step further, we get into what FERC Order 881 requires, and that is ambient adjusted ratings. And that is where you consider the temperature on the conductor. So the ambient temperature on the conductor, as I mentioned, it's around 1 degree capacity, 1% capacity improvement for every 1.8 degree Fahrenheit change. So we can see that typically this has a pattern of day, night, day, night. In the day, the rating goes down. In the night, the rating goes up. And then the last frontier is dynamic line rating, where you do all of the above, but you then include the wind. And this now doesn't have a standard day-night pattern, because wind really changes day, it's not dependent on day and night. It's changing all the time. It's a lot more volatile and flexible, but you can get a lot more gains. And as you can see there, you can get anything from 10 to 50% gains the majority of the time, depending on how windy this area is and what orientation the line is against the wind. Whereas AAR only gives you typically 5 to 10% gains overall. So typically, when you look at DLR or AAR or any sort of rating, you're moving from something that is a static rating for all time, and you're moving that to a statistical rating. So it's a rating that you know, it depends if the weather is conducive to that. So if you look at this chart here, it's showing percentage of time on the x-axis versus the relative rating on the y-axis. I've said that it's percentage, but in reality it is per unit. So when you see 2.5, that's actually 150% gain on the static rating in this particular example. Now, I've chosen in this particular example a really great line, right? This line is in the Nordics, so it's cold, it's windy, and the static rating was quite conservative. So this is a really great example. There are other examples where you don't have such extreme gains, but bear with me. So at the end of the day, what I have here is I have my static rating at 100%, and I can get my ambient adjusted rating or ambient temperature rating in the light blue, and then my DLR rating in the green, and then I can get a forecasted rating of the DLR in blue. And you'll note that the forecasted rating is a little bit lower than the DLR rating in real time. And that's done on purpose, because one of the worst things you can do for the market is to forecast that, you know, in 2 days that there's going to be capacity, it's going to be a windy day. And then as you move into real time, you realize it's not going to be a windy day, and you then have to curtail. So 2 days in advance, you book the generation, you pay for it, and then as it gets into real time, you have to do redispatch. That's doing the opposite of what we're trying to do here. So if our forecast is always conservative and it gets higher as we come into real time, that's exactly what we want, and that's how it looks here. But you can see that, you know, 50% of the time in this particular example, you have 75% gains. A small percentage of the time, 20% of the time, almost 100% gains. And then in this case, you know, above 95% of the time, you are still getting in the region of 30 to 50%. As I say, this is a really good line. Not every line is going to give you this amount of gains, but there are always gains to be had. So let's talk about the benefits. I know we've got a lot of policy people, we've got a lot of utilities here that maybe understand DLR already, and they want to talk about, you know, how does this change our lives? So let's start off with an example, a real example, and let's talk about utilities. Well, the first thing I would say is when I started working for Ampacimon and thinking about DLR, I always thought it's an absolute no-brainer. You know, it's you get extra capacity. You push your equipment a little bit harder, but you know exactly how far you're pushing it. You know how close you're getting to the edge, and you can get a whole bunch of extra capacity out of it. It makes so much sense. Surely people are buying this by the hundreds, by the thousands. And look, there are a lot of people buying this, but it's not mainstream, okay? And the reason why it's not mainstream is because of the benefits between utilities and society. Who benefits versus who pays? This is mismatched. Let's talk about utilities first. So in this particular example, this is a slide taken from PPL, amended slightly just to make it relatable. So they had a project where they were looking to reconductor a line, or potentially build a new line, or look at dynamic line rating. And they were assessing these against each other. So the time to implement a reconductoring is 2 to 3 years with lots of outages and a cost of $0.5 million per mile. That gave them a total of 34% extra capacity. Rebuild, 3 to 5 years, extended outages, and way more per mile, but it gives you a full doubling of that capacity. I will add that these numbers are quite optimistic. With the supply chain issues that we see around the world on certain, well, there's a lot of people trying to buy conductors at the moment. These lead times are in Europe up to 12 years now, which is not great. We then have dynamic line rating. We are able to install this live line in less than a year, so there's no outages. And this is where I've changed PPL's slide. So PPL had 1 million as the total cost. This particular line they were talking about is a 15-mile line, so I just divided that, and it gives you approximately 70K per mile. That's probably a bit of a high estimate. It might be cheaper than that in reality, but gives you a good ballpark to measure against on a common plate. And that gives you, in this particular example, they had a 10 to 30% extra capacity on that line. So in this particular case, even if they were going to reconductor, it bought them some time. They were able to get a little bit extra capacity and defer that asset upgrade. Similarly, in some cases, on some of the lines, they've been able to put DLR and completely negate the need to reconductor just because of that extra, 10 or 20%. So I always like to show this slide. I don't know if PPL's in the call, but whenever I show this slide, I always say, look, they're smiling and they're happy. It must have worked, right? But anyways, this is the DLR sensor installed in the line. But one of the things that they boasted was they had 3 lines DLR installed. And when they did the study, they predicted that in 2025, they would have a constraint payment. So the benefit to the consumer would be 23 million in 1 year saved on congestion costs. Well, what's interesting, if I go to this slide, so assuming a regulatory incentive, on the consumer side, PPL has just released a statement to FERC regarding DLR, and in that, they mentioned that between 2022 and 2023, there was a savings of around 64 millions, or a difference in constraint payments on that particular line between 2022 and 2023 of $64 million of constraint payments. That's a massive relief on the consumers. But what's interesting is that's not what benefits utilities, right? Because the incentive to utilities they're not always aligned in terms of the consumer. The consumer gets the benefit, but the person who pays for the DLR is the transmission asset owner typically. So if we look on the left-hand side, most business cases and return on investment cases for DLR is done with assuming no regulation incentive. So this is based exactly as PPL did it. They look at the lower cost against traditional rebuild or reconductoring, okay? Now they're not comparing apples and apples because a reconductoring is a constant 34%. A rebuild is a constant 106%, whereas DLR, it depends, okay? But they can try to do a comparison on that. Another advantage is improving outage windows. So even if they were to do a reconductoring, they would be able to put the DLR in and be able to do that reconductoring with less disturbance and disruption to customers by improved outage windows. Of course, one of the biggest ones is deferral of asset build. So they plan to build the assets, they plan to reconductor or rebuild, but they just want to save themselves 2 or 3 years, and there's some big financial implications on that. And then lastly, they have quantified risk. So they believe that they are pushing their assets. They're worried about, for example, heat waves or assumptions that they've made in the past, and they're justifying monitoring those assets in real time with actual conductor temperature and understanding the risk to their assets. When they weigh those numbers up, you typically land up with a return on investment timeline of 2 to 3 years, okay? Which is reasonable. It's enough for you to justify a project, but it's not going to justify a project in all cases, and it's not going to justify a project in all constrained cases. So the consumer is definitely, there are a lot of places where the consumer could be winning, but the utilities are not taking it up by themselves because of this return on investment. If you were to somehow include the consumer benefit in incentives for the transmission asset owner, the return on investment timelines go to a mediocre, okay, this is assuming the full benefit was associated with them, but it would be in the order of 2 to 3 months max, okay? So the benefits on the consumer are absolutely astronomical. The benefits to the utility are fairly humble and need to be justified. So where we sit today, just to summarize, a lot of the times people hear DLR and they think this is really cool. This is a new innovative technology. We should really do an innovation here. And in reality, that's not really true. DLR is well proven. It's TRL level 9. It's got operational deployments around the world, which I'll talk about. I've got some case studies. So on the technical side of things, we've done lab tests, we've done field tests, we've got operational solutions, we've got technical documentation that's been peer reviewed. We've got competition. You know, Ampacimon's not the only DLR supplier out there. There's other suppliers. In terms of systematic processes, in terms of getting this implemented, cybersecurity is always a concern with any system that you have, but this has been addressed. As I say, with PPL, we have this. We are NERC compliant. This is possible. Data connections, absolutely possible. Using this in real time or forecasted use. This is already being done by PJM and PPL for the last few years, and also with FERC Order 881, which we'll talk about a little bit. This is really setting the standard. As soon as FERC Order 881 is passed, that systematic process should be solved. Every utility in the US should be able to have these systems in place. So I don't see those. Sure, at the moment with FERC Order 881, we're kind of in the process, but after July 2025, we really should have, that shouldn't be a blocker anymore. The last final blocker is financial. And as I mentioned, who benefits and who pays? As I say, it can still justify itself even as just a utility. It's a little bit more difficult to justify. You've got to do a bit more number crunching. It could potentially work, and you do have some really good utilities around the world that have done that and have justified the projects as such. But of course, having regular incentives or mandates. So depending on your style, you want to have a whip or a carrot, it depends. There's different ways to do it, but they achieve the same goal at the end of the day, that the consumer gets the benefit. And we are all consumers. We all have electricity that we have to pay. And if the price can be kept reasonable, that makes sense. So talking about some of the work that's been done in the US on the FERC side, really my hat's off to FERC and the US. I work in Europe as well, and you know, I think in Europe it's a lot more complicated, a lot more parties involved, a lot more opinions. And certainly I would say that FERC is leading the way on this. So congratulations on that. FERC Order 881 was released in 2021, and the full compliance is due July 2025. What is required here is ambient adjusted ratings. So we don't include wind. You could include wind if you want, but it's not compulsory. And you need to give a forecast of a 10 days horizon, and you have to include emergency ratings and normal ratings. And present this to your RTO ISO. So that full communication system, which I presented as a potential hurdle, that is what will be resolved by 2025. What will not be resolved is the additional capacity that you can gain from wind. So when I started this presentation, I spoke about wind and I spoke about ambient temperature. The interesting thing about wind and ambient temperature is that ambient temperature is quite easy to do from a software point of view. If I have a weather provider, so the same person who does your weather forecast for your phone, Google or IBM, or insert weather provider here, the way they work is they have a bunch of weather stations around the country in all the major cities. And then between those cities, they interpolate or use some sort of model to fill in the gaps in the measurements between those weather stations. So they'll have two cities, let's say 100 miles apart, and they will use this model to fill that in. Now, if you look at ambient temperature, that's very easy. You could have, let's say 90 degrees Fahrenheit here, and you could have 89 degrees Fahrenheit here, or 85 degrees Fahrenheit here in this city. And you interpolate the two, you land up, you know, with some number in between. You know, you might be a few degrees out, but in terms of rating percentage, you know, you got an error of like, you know, 1 to 3% maximum, no big deal, right? But if you were to try to interpolate wind, which is what they do, so you get wind in this city, you get wind in this city, and then you try to work out exactly what the wind is, the wind speed, the wind direction, at every spot in between that, those two points. This is not so easy. Okay, this is really, really difficult to get right in real time, and even worse to try to get this right as a forecasted value. So if you go to a weather provider, you can get wind data, you will get wind data, but it is not necessarily accurate. And when I say accurate, it's got to be, it's basically, it could be incorrect in the wrong way. It could be optimistic. So it could say that the wind is blowing when in actual fact the wind is not blowing. And that's exactly what you don't want when you're doing ratings. So this is where DLR is. The step between AOR, the step with FERC 881 and DLR, in terms of science, is quite a big step, right? Because you need to add wind. And how do I get wind? I can't just use software. I need to use something else. And that's where we put sensors on the line, and you know exactly what's happening on the line. You can measure the wind on the line at each location, and then you can forecast it as well and correct the error that you see in the data from the weather provider. So you're moving from a software-only solution, which is quite readily accessible, lots of competition, lots of people can do this sort of thing, IEEE standard, moving to a sensor-based solution that needs measurement at local areas all the way along the line. That being said, FERC is eyeballing a NOPA towards the second half of this year, I believe. I mean, I don't want to put words in FERC's mouth, but this has been on the cards for a while. And don't quote me on second half of 2024. This is just my opinion of the timeline. But the most important thing is that they are looking to mandate DLR, because the benefits to the consumer, as you could see from wind, are really there, right? Once you add that wind, you can get a lot more out of it. The draft points that they were looking at, as I say, don't quote me, this is just how I see it, is there will be some sort of congestion definition. So what is congestion? And the assumption there would be, you know, some sort of congestion costs on a line over a period of a year, maybe 5% or something like that. They would be looking potentially at wind. So in my personal opinion, you can get quite a lot of gain even if the wind is low. So this doesn't really matter, but you know, it's one way to look at it. We have wind forecasts of the country, all around the country, and most areas have enough wind to produce decent gains, but they would look to potentially put a wind requirement on there. And then maybe, I don't know, this is just my opinion, maybe they will enforce the use of sensors, maybe they won't, I don't know. But if you want to measure wind, you normally have to have a sensor if you want to do it properly. But what we do know is it will most likely be a mandate and not incentive based. That's what I understand. We've had two public documents come out quite recently, one from PJM and the other one from PPL, talking about the support of DLR. PPL was very supportive, mentioned exactly like I said, 64 million congestion saving on the lines. What they were against was mandating that. It's like they were saying, look, we do it anyways, we've got the tools, no one likes to be told what to do, I can understand that, and they were doing it anyways. But I do kind of feel like if you don't mandate it or if you don't incentivize it, the existing requirements for most transmission asset owners is not enough for them to justify that return on investment and prioritize this over other things that they look at, my opinion. All right, so that's that. That's setting the framework. I'm going to go into some case studies for the next 15 minutes, and then I will open the floor to some questions. So here's some case studies. The first case study we have is in Elia, Belgium, where they basically have flows. So Belgium's in the middle of Europe, and it's got Netherlands on the top, and it's got France on the bottom, and the power has to flow through this country. So they have quite strong flows through the country, and they wanted to add offshore wind feeding into Belgium. So they put DLR on some of their 380 kV lines and got up to 30% extra capacity. And this did two things for them. Number one is it avoided tap changing of phase shifting transformers. So there's an asset health saving there. But in terms of international redispatch, they have an example of where this DLR saved 500,000 euros of international redispatch in one day. So the numbers are quite big. This is quite an interesting one that we see because quite often I get the question of, can you use DLR in planning? You can use DLR in planning, but you just need to be very careful and you need to understand your process. And it's not simple. You've got to just have a process, just the same as if you were to use wind farms versus a diesel generator. A diesel generator is able to produce whenever you want at full capacity. So it's a capacity thing. Whereas a wind farm, you have to do studies, you have to work out when the wind's blowing, you have to do all your financial investigations based on that. That answer, that has been achieved. That was considered a challenge back in the day, but it's done. Same as this. Comparing a line upgrade is just a static thing. I spend this, I get this. Whereas DLR is like, I spend a much smaller amount and I get a flexible value between the two. Anyways, so in this particular case, I've got, there was some, again in Elia 2012, they were bringing in a wind farm into the area. Once the wind farm connects into the grid, there were inland congestions. So this is your normal network congestions, not the cable from the wind farm into the land. They put the dynamic line rating on, they integrated it through to their SCADA, and they got 20% extra capacity 90% of the time at low wind speeds, less than 5 meters per second. So this was really, really good because wind farms and DLR go hand in hand very, very well. Because if you're in the same area as the wind farm, if the constraint's in the same area, when the wind is high and producing energy, it's also producing more cooling on the line. And that capacity is exactly when you need it. But that's not the only case. This example here, EDF, we have in France, same example, but with a solar plant. So here you can see a solar plant. You can see that every day when the sun shines, it would kind of hit a maximum. And you would see that it would exceed the static rating on particularly sunny days in summer. If they included DLR, they are able to run it at its full output without any curtailment. And that gave them a good solid 15% extra capacity and enough to justify the project. This one I love. It's kind of a weird example, but I just like it in the planning realm. I just think it's cool. But essentially what happens is in the French Alps, they wanted to build a ski resort. And when you build a ski resort, you have to say, okay, well, I want an electrical connection. So they applied for an electrical connection and they were told, look, if you want the connection, we're going to have to build another line because we can't facilitate that ski resort with this equipment. But then what they realized is, hey, hold on, it's a ski resort. It's only going to be using electricity in the middle of winter. So they worked out, actually, if I use the winter rating, I can justify this build. So this is a planning thing. They justified the build and they put DLR on the line to monitor the line and to also ensure, not just with planning studies, but actually monitoring it and activating that extra capacity. So they were able to build the ski resort without needing to build any extra line. So 40% extra gain, obviously, because it's in the middle of winter. I don't know, I just like it. It's a really cool practical example. Over here, we've got another example of wind farms and renewable generation connection, but this one is showing a slightly different thing. So over here, we've got a connection, and the question was, can I connect more renewables at an existing connection point and take a lower curtailment value if I include DLR on the line. So essentially what you're looking at in this chart here is I've got installed wind capacity. So how much wind generation can I include, and how much curtailment am I going to accept along the way? So you can see here with just normal static line rating, I start to shed at about just shy of 200 megawatts capacity. But if I add the DLR, I can get all the way up to just shy of 250. So sort of 100 extra megawatts. So 50% extra hosting capacity, and with 15% less curtailment. So this is a no-brainer really for building extra capacity on a connection that already exists, and it can justify the financial. And this is the financial studies that are done in order to install more wind farms on an existing connection. And then lastly, this is a slightly different angle. This is more of a utility angle. This is where utilities are less worried about gains and more worried about how much they are sweating or risking their assets. So over here, they realize that they've got ratings that were maybe made 30 years ago, and they were worried that with climate change and heat waves and all of these other things, that maybe our assumptions aren't that valid. So what they did is they put the DLR sensors on, not to actually get more gains, but to understand the risk on the conductor in real terms, not paper exercise, but basically monitor the thermal loading on the lines, understand if they were pushing them. So here you can see the summer heat wave, 40 degrees Celsius maximum, so that's about 100 degrees Fahrenheit somewhere, no, 110 degrees Fahrenheit, somewhere there. As you can see, as the temperature went up, there are certain periods where they were really in the risk zone. The DLR was really going down quite low. And this is something that on their existing assumptions, they needed to be cautious, and they needed to change some of their planning processes, some of their capacity numbers that they were using. And that is that. So to summarize, wind is the key, in my opinion, to, well, it's not an opinion, it's a fact actually. Wind will give you much extra capacity compared to AAR, even though AAR does give you gains, okay? So wind is a key part of that. The only accurate way of getting hold of wind today is with local measurements, whether that's with sensors or weather stations, but those weather stations have to be very close to that tower. You can model some of these things, but when you model them, you've got to accept certain risks, and you've got to then be conservative. And when you're conservative, you are going to lose some of those gains. DLR is commercially available. It's not a low TRL level. We've got, you can see from the case studies, multiple case studies around the world where this has been used. In some cases, some of the cases I've shown you from wind farms are from 2012. Okay, this is 12 years old. So it really has been used around the world. It's not an innovation. I understand that even if it's a well-known technology, some people need to get up to speed with that, get familiar with that, but that's more of a business process question and systematic question rather than a does the technology work question. Adoption is lower due to the lack of regulatory incentives and greater complexity. Now this is, please don't take that as an insult, I'm talking globally here. So around the world, you know, we see this problem of who benefits, who pays, and it's not an easy problem to solve. And as I say, FERC really is leading the way around the world. Yes, it's more of a mandated way rather than incentive-based, but it's really good to see the work that's happening in the US. But this is definitely one of the things that's holding back wider adoption and holding back consumer benefits. And then last point is, even without regulation, there is decent return on investment, although, as I say, this is really dwarfed in comparison to the savings to the consumer. So if there was some way of bringing that consumer benefit into the utilities, I imagine you would open the floodgates and utilities would look at this a lot more carefully. So hopefully I didn't say anything too offensive. Hopefully this is just reality. But yeah, let's park it there and we can answer some questions.
Well, great. Thank you, Brian. Really appreciate your walking us through all that detail. It was very interesting, and I'm starting to get a few questions that are coming in. Let me pull them up and we'll clear those out. And then I've got some of my own. In the meantime, for folks who are watching, if you have any other questions, please feel free to go ahead and put them in the question function, and I'll make sure that we run them by Brian for his reaction and response. And the first couple of them are really kind of focused on specifics around the sensors and use of sensors. And what they're asking is, do you have to have multiple sensors per line section for the wind measurements? And if you do, how far apart do you have to place the sensors to get accurate wind readings for the length of a line?
Yeah, I mean, it's a good question, and it's a very common question that we get. So essentially the way we do our work is whenever we are looking at a line that will have DLR on it, we take that line, basically the customer will give us the GPS coordinates of each tower along that line, and they will tell us the conductor type and the conductor information. We use that and we bring that into our system, and we study the last year worth of weather data from January to December. And we can actually work out from that where the wind was, what wind direction, typical values. And from that, we do a study. We calculate the what we call the critical spans. And then we would put one sensor per critical span, typically. Okay, now what does that mean? That's a very it depends answer, right? But to give you a rule of thumb, it's typically one sensor every 10 kilometers. So that's, I don't know what that is in miles. I don't know, 7 miles. I don't know. I'm guessing. And I don't know, something like that. One every 10 kilometers, and then because it's very dependent on the wind direction, if the conductor or the line changes the direction by more than 15 degrees, we would typically put another sensor there. On average, you know, from all our lines all around the world, and that's some lines are you know, 100 miles long, some are, you know, 10 miles long. The average is typically around 6 sensors per line when we add up all of them and divide them by the number of numbers. But yeah, small lines like 10 kilometers, 10 miles or so, that would be like 2 or 3 sensors.
Okay, well, I'm starting to get a few more coming in here. Another question is, what are the impediments or concerns, setting aside regulatory incentives for utilities implementing or using DLR at scale? And they suggest that maybe part of the answer has to do with partnering and purchasing data from weather stations. Can you speak to some of the concerns other than regulatory incentives?
Sure. I mean, that's a really good question. Okay, so I think the biggest blocker is obviously change. Change is a difficult one. And I don't say this in a judgmental manner. You know, we've got a lot of change going on in the electrical sector, but having new business processes, having things that you know, have been like that for a long time and have worked quite well, it's quite difficult to move away from that and feel confident about that. So there's quite a lot of user engagement and multiple people within a utility that you need to speak to and get on board. So it's not small in terms of the business processes that need to be done. That's number one, change management. In terms of other impediments, I would say that obviously system. So in the past, so like if you had PPL before FERC 881 came out, you know, we had to get the sensors up and we had to get the data, and we got our rating system up. Fine, great. Now we have the rating data, it's coming out every 5 minutes or every 10 minutes. What do I do with it? How does it automatically go into my system? So linking those systems, my SCADA, my planning systems, changing my business process in terms of outage planning, these things are, you know, they make sense. They're natural. You have to do them. You kind of see how they work, but it's not simple, and there are quite a few stumbling blocks along the way. It can be quite a big project. So that part is not easy. So the system integration, where does the data go? How does it link? I suppose there is a level of mistrust in the technology, and hence why people always go through their own lab experiments and that sort of thing. I think that's just a cultural thing. A lot of utilities want to do their own labs. There are a lot of resources out there of lab tests and that sort of thing that you can use. Talking about the last point around weather data and partnering with solution providers and that, I don't know. I don't know if that's really a blocker. I think that can be a blocker depending on the solution provider's business model. So if your solution provider is absolutely against on-premises, that's a blocker, right? Because you've got NERC SIP, and that's difficult for utilities to work around that model. Utilities like to work, even with their software, they use CapEx, not OpEx. And a lot of providers provide solutions as OpEx. That's not always conducive to the way that utilities work. So it's not well, maybe it is a regulatory thing, but that's something that I think people struggle with, because utilities are trying to reduce OpEx overall. There are some ways around it, but you know, I think if it's a cloud only, software as a solution only service, this is more difficult for utilities to swallow.
I got a question that I want to go back to some of the case studies you had where they were focused primarily on Europe, and ask you about your differences in experience between working in Europe versus working in the U.S. You had several examples in the case studies of usage in Europe, and I'm just curious as to what do you attribute that to in terms of, it seems like there's more use or openness to using the technology in Europe as opposed to the US maybe right now. And I'm just curious, in Europe, are there specific incentives that are being used, or is there a mandatory approach, or what do you attribute that to?
That's a very deep question. I think first thing to be careful of is, you know, me showing a lot of European examples doesn't necessarily mean that Europe is more advanced. It might just mean I have more European examples, really. I think there's a few different things. Number one, the first thing to bear in mind is the difference between distribution and transmission. This is something that people overlook quite often. In the US, you know, this is typically split at 33 kV, which means that distribution really is the low end overhead lines, the last few miles of the line. Whereas in Europe, distribution is typically split at 132 kV. So you have some of those incentives, you know, like the distribution guys are able to spend a bit more money and can kind of move in that sub-transmission level a bit faster. They're not big, slow transmission systems. That's one of the things, minor one. In terms of regulatory incentives, where Europe is maybe better than, well, actually, I don't know if I can say that strongly, but Europe has got a lot of innovation funding. Okay, so there's a lot of funding that is set up that allows for innovation, which is new products, maybe a product that exists, but you want to try it in your particular region. That is classified as innovation. So a lot of these projects, which are closer to BAU, they are actually using them in BAU, but they use innovation funding to pay for that, and that's something that's done. I mean, that's not something to be proud of, in my opinion, right? Because you're using the wrong money for, you know, you kind of, if you get it right, you want to use BAU money for BAU stuff, right? You don't want to be bypassing that with innovation funding. And then I think there is potentially, maybe in Europe, there's a little bit more a little bit more closer to the innovation realm. I think some of the DLR stuff, you know, we are European, we've been working there since 2010. Maybe there were just more murmurs in the European area than in the DLR space than in other places. So that's my thought. I don't know.
Well, so I got a real mix of kind of pretty high level philosophical questions and then some really specific granular ones. So, and I've got another one here, again, back on sensors, saying, do these sensors mount on the conductors or the shield wire?
They mount on the conductors. Very good question. And they measure the conductor current. So yeah, they're measuring, and they have to, because they're measuring the conductor temperature, and that's the shield. The shield doesn't, you know, doesn't heat up. It shouldn't have current on, too much current on. Yeah.
Okay. This question goes towards the example you have with PPL, and they're saying for the reconductoring on PPL, were they going back with the legacy type of, where they were going back with the legacy type of conductor, or were they going back with more advanced conductor composite core to do that? And the question says, most typical advanced conductors provide a 100% rating increase.
Absolutely. Look, I mean, advanced conductors to me are another no-brainer, right? It's another one of these things which is like filed as an innovation, but to me is not an innovation. It's been around for many, many years, and it's tried and proven. There may be some challenges, I suppose, but you know, this is something that could be considered. In terms of PPL reconductoring with advanced conductors, I honestly don't know if that was an advanced conductor or just a thicker conductor. Sorry, I can't answer that, but in my opinion, they should have considered advanced conductors. Yeah.
I actually thought it was interesting when your chart kind of lays out the different options and alternatives that PPL was looking at, and over and over again, we keep hearing people just assuming that, or kind of questioning whether utilities go through that kind of an analysis where they look at various alternatives and see what the different pros and cons are, including looking at things like DLR and different advanced technologies. So I thought it was interesting for you to kind of map out what seemed to be the thinking that PPL undertook with that particular project. So
yeah.
Let's see. Here's a question: Is it possible to integrate a DLR system into an asset management to calculate and monitor the health of the line?
Absolutely. It's a different thing. So here you're bringing in different parameters. So you bring in conductor temperature. One of the things our sensor monitors is vibrations, so we can work out stress. We can estimate asset life. So yes, I call this value add. So it's another reason to buy the equipment, and some people buy this equipment purely because of that asset health component. But yes, that is a component of it.
One more question. We're getting kind of close to the top of the hour, but I'll try and hit some of these. How do you differentiate from non-contact sensor competition?
I mean, how political an answer can I give here? I mean, I've got my opinion. I don't want to badmouth anyone. Okay, so at the end of the day, look, if you are putting DLR in a system, you know, you need to worry about maintenance and longevity. Okay, so there's two parts to getting this in. The one is, how do I install it now? But then also, how do I maintain it over the next 10 years, right? So with non-contact, I can get it in very quickly. I don't need an outage. I don't need, you know, I can run there. I can go to the tower and I can put it on. The problem is, because it's on the tower and I have a solar panel and I've got batteries, those solar panels and batteries potentially need maintenance. This is just reality. If this is something your company can manage, great, you know, absolutely, no problem. But in our case, what we do is we put the sensor on the line, and it's completely self-maintained thereafter. So it installs, it's powered by the line. There's no batteries inside it, so the degradation is limited. They're designed to last for 10 years with zero maintenance. So that's really, it's the overarching low maintenance side of things. because we are closer to the line, we're measuring exactly on the line, we would argue that it is more accurate. But in reality, as I say, I don't want to badmouth anyone. I'm sure non-contact can work. I'm sure it's a feasible technology. So.
I think you navigated that one pretty well. So, and I think that's probably a good one for us to start wrapping up the presentation. And let me thank you, Brian, for spending your time to kind of walk us through this technology and field some of the questions around about it. I wanted to mention to folks that we will post the webinar on our website, so folks can watch it again if they like, or if they didn't get a chance to see it, or if they know folks who didn't get a chance to see it, they can have them look at it on the website. So thank you very much again, Brian. Really appreciate your coming in and talking to us. And as we wrap this up, I want to mention for folks that we're looking ahead to having our next webinar on March 19th. And the presentation is going to be done by power engineers, and they're going to focus on ballistic threat projection, which I think would probably be a really interesting topic to hear about as well. So Brian, let me thank you again for coming in here, and I want to thank everybody for their attendance at today's session. And with that, we're going to call this one a wrap. So thank you very much.
Yep. Thanks, guys. Bye now.
Bye now.